So, well, here I want to introduce a useful lemma. It says that let p of t be a polynomial with real coefficients and lambda a complex number. Then I have that lambda is a root of p of t if and only if the conjugate of lambda is a root of p of t. And well, the proof is very simple, and actually the consequences of this lemma are very, very useful. So the proof of this is this. I'm going to set p of t as a polynomial, so I will write it in the form a m t to the m plus a m minus 1 t to the m minus 1 all the way up to a0, right? So in this case, I'm stating that p of t is a polynomial of degree m, where ai is a real number for I from 0 up to n, right? So all the coefficients are real numbers. Well, if we work under the assumption, if we assume that p of lambda is equal to 0, so namely that it is a root, we have under this expression that am lambda to the m plus am minus 1 lambda to the m minus 1 plus all the way up to a1 lambda plus a0 is equal to 0. Well, now I'm going to apply the conjugate onto this whole expression. And we'll see this. We have that am lambda to the m plus am minus 1 lambda m minus 1 plus a1 lambda plus a0 is equal to 0. Conjugate. Well, but the conjugate of 0 is 0 itself. Now, the conjugate is in some sense a linear operation because if I have the sum of two complex numbers, then I can split into the sum of conjugates of those complex numbers. So this equation that I have here becomes this am lambda to the m plus am minus 1 lambda to the m minus 1 in conjugate plus all the way up to a1 lambda conjugate plus a0 conjugate equal to 0. Now, let's continue on this. The conjugate operation also is commutative with the product operation. So I can split this and write it in the following form. Am conjugate lambda to the m conjugate plus am minus 1 conjugate lambda m minus 1 conjugate plus a1 conjugate lambda conjugate plus a0 conjugate equal to 0. But well, let's see. All of these numbers that I have here as coefficients, all the a's, are real. So the conjugate is itself. Take, for example, 2. What is the conjugate of 2? It's 2. So in this case, well, I have that each of them are just the a's. And this lambda powers, well, I just apply the same rule that I can break the conjugate as a product, and it becomes this am lambda conjugate to the m plus am minus 1 lambda conjugate to the m minus 1 plus a1 lambda conjugate plus a0 equal to 0. Oh, but this says that exactly this says that p lambda conjugate is equal to 0, so it is a root. Actually, I can reverse the arrow and go in this direction, and well, that completes the proof of this. Now, some corollaries out of this one in the following sense. So if lambda is a root